Hi, today I am going to discuss about basics of DC motor, DC generator and induction machines. Basic means here only we will discuss that how EMF is induced in these machines. Last class we have discussed about how EMF is induced in case of transformer. The same equation, same structure here also we will consider and will explain the EMF generation across the machines. So let's start. These things already discussed. Faraday's law, E proportional to rate of change of flux linked with the coil. Psi is equal to n into phi, n number of turns, phi flux in wave. Direction of the induced EMF will be always to oppose the cause, and the cause is nothing but change in flux linkages. Flux linked with the coil. First of all, we have to understand that how the flux linkages can be changed associated with the coil. There are three ways. First case already we have discussed in case of transformer, where we have kept coil stationary and changes the strength of the magnetic field. Here we will keep the strength of the magnetic field constant, but will change the position of the coil, or the coil will move in one direction. Third one also today we will discuss that varying magnetic field we will generate. At the same time we will allow to move the conductor. This structure already we have discussed in last class, that B is flux density, flux per unit area. These are magnetic lines of force coming out of the screen. This is direction of the current, this one moment of the conductor. In case of transformer, this was absent. That means conductor was stationary. But here we will allow the conductor, or we will move the conductor in this direction. Current will continue to flow in the same direction. At the same time, the strength of the magnetic field we will keep constant. So as the conductor is allowed to move, or you can say a current carrying conductor is placed in a constant magnetic field, then the conductor will experience a force, and according to Fleming's left hand rule, conductor will move in this direction. So we will assume that conductor is moving in this direction. Based on that, we will try to find out the EMF induced across the terminal of this single turn coil. So B is equal to uniform flux density in Tesla, N is equal to 1, rectangular loop of one turn, L is equal to length of the conductor, X movement of the conductor. The flux lines, conductor and the motions are mutually perpendicular. The flux linkage of the loop B into L into N Webers. Now based on this equation, we will discuss the operation of motor. So second condition is that moving the turn outside the region of a static field. So let's see this. This is your constant magnetic field and the conductor is moved in this direction. B is equal to uniform flux density in Tesla, N is equal to 1, rectangular loop of one turn, L is equal to length of the conductor. Moving the turn outside the region of the static field. So in this direction we are moving. As the field is stationary, as the magnetic field strength is constant, so we can assume B is equal to Bm. This is constant, and conductor is moving with the velocity v. Then the EMF induced E is equal to rate of change of flux linked with the coil, and that is equal to ddt of Bml into N into X. So in this case, flux linked with the coil becomes Bm into L into N into X. But in case of transformer, it was not there. X was not there, movement was not there. Okay, so unity, or you can say X is equal to 1 in that case. Okay, So ultimately induced EMF is coming as Bm into L into N dx dt, and dx dt is equal to velocity of the conductor is equal to B. So this much amount of EMF will be induced across this rotor. So we have seen that keeping the magnetic field constant, if we are moving the current carrying conductor, then also EMF will be induced. In case of transformer, we have seen that we have kept this coil stationary, but we have created a varying magnetic field. Then also EMF is induced. Let's proceed. As the conductor is moving, this EMF is known as rotational EMF or the speed EMF, and it is found in case of DC machines and alternators. So in case of motor, a current carrying conductor is placed in a magnetic field, and this magnetic field in case of DC machine can be developed using a electromagnet or a permanent magnet, and then current carrying conductor is placed in a magnetic field. Then we will see that based on Lenge's law, the direction of the induced EMF will be such that to oppose the flux linked with the coil. Now to reduce the flux linked with this coil, the conductor starts moving in this direction. So this is the basic of DC motor. Let's see about induction machine. Here the third case we are going to discuss. Moving the turn and changing the flux simultaneously. That means this magnetic field is of variable in nature. At the same time the conductor will move. Then how the EMF will be induced? So to explain that, let's take B is equal to Bm cos omega t and conductor is moving with a velocity V. Then the EMF is E is equal to dψ dt. Now in this case, flux linked with the coil becomes Bm cos omega t into L into N into S. And E is equal to minus of Bm sin omega t L N omega x plus Bm cos omega t L N B force. So here both transformer and speed EMF are present, and it is employed in case of induction machine and AC commutator machines. So let's discuss a little bit about this induction machine. In case of induction machine, single phase on three phase, a rotating magnetic field is developed, and that rotating magnetic field is created by applying a AC supply across the stator winding. Then the rotating magnetic field will cut the rotor conductors or rotor number of turns, or you can say rotor. Then an EMF is induced across the rotor because the magnetic field is of variable in nature and the rotor is stationary. So in this case, transformer EMF is applicable. Now, as soon as the EMF is induced across the rotor conductor, then as per Lenge's law, direction of the induced EMF will be to oppose the cause, and the cause is flux linked with the coil, or changes in flux linked with the coil. Now to reduce the changes in the flux linked with the coil, rotor starts moving in the direction in such a way to reduce the flux linked with the coil. So this is the basics about induction motor. In more detail we will see when we will discuss about the speed control of induction machines. So in case of induction machine, both transformer and speed EMF are present. Transformer EMF is present when the rotor was just about to move, and when rotor starts moving, then rotational EMF is found in the machine. Okay, so today in brief we have seen how EMF is induced in case of DC machine as well as induction machine. In case of DC machine, we have seen that rotational EMF is present, but in case of induction machine, both rotational and transformer EMF is found. Transformer EMF is nothing but conductor is stationary, but the magnetic field is of variable in nature. And the rotational EMF is when magnetic field of constant strength, but conductor is moving. So as it is fundamental of electromechanical devices, so we are not going in detail about the motor parts or in detail about the workings of these machines. As the time passes, we will discuss step by step about these machines. Thank you.